Lesson 82, we'll be looking at limits and continuity and differentiability and some relationships between those things. So we have three functions here, f of x, g of x, and h of x. And we're looking at limits a little bit here. So for f of x, the limit as x approaches the value c as we get closer to c from the left and from the right does not exist. The reason it doesn't exist is because they are approaching different y values. Over for g of x here, the limit does exist as we approach c because the left-hand limit and the right-hand limit are the same, but f of c doesn't exist, so it's discontinuous there. It's not continuous at c. On h of x, the limit as x approaches c does exist because the left-hand limit and the right-hand limit are the same, and f is continuous at c because f of c equals the limit as x approaches c. We are going to take a look at one of our definitions of derivative, and we have two illustrations here, but of the same idea. Here we know the derivative is the slope of the tangent line to a curve at any point on the curve. In order to find the slope of a line, though, we need 2 points, and so if we have a tangent line, we usually just have 1 point on that tangent line. So if we drag this down here, it looks like maybe this is the tangent line, but we only know the 1 point here. So what we do is we take the slope of a secant line. So here, this fraction here is the slope of the secant line. So for slope, we know it's y sub 1 minus y sub 2 over x sub 1 minus x sub 2, and that's what we have here. We have a y value minus a y value over the x value minus the x value. So this fraction, not talking about the limit, but this fraction is the slope of the secant line. Obviously, derivative is the slope of the tangent line, so what we do is we let this x value get closer and closer to c. So as x moves closer and closer to c, we would be getting, so if we had x here, this would be f of x. We would have a line through there, which looks closer to the tangent line. And then we could move x even closer. Maybe have x here. So here's the y value right there. The secant line looks like this, which looks even closer to the tangent line. And so what we do is we use that secant line, but to find the slope of the tangent line, which is the derivative, it equals the limit as x approaches c of f of x minus f of c over x minus c. So that's our definition of derivative. Now what we're doing, we went over that so we could look here. If we wanted to find the derivative at x equals c here, if we use this x value, and as this got closer to c, we would just, this tangent line would be getting closer and closer to looking like a vertical line, and then over here, the tangent line would not be the same as the tangent line coming from this direction, using this x approaches c idea. And so we say that to help us realize that for a function to have a derivative at c, it must be continuous at x equals c. So it's got to be continuous. We can't have one of these jump discontinuities here or something like that. So in order for a function to have a derivative at a certain point, it must be continuous there. There's some other stipulations, but it definitely has to be continuous. Another way of saying that, if f prime of c exists, the derivative at some value c exists, then the limit as x approaches c of f of x must be equal to f of c. Really what this is saying is it must be continuous at c. So that's some more, it's not much application right there, but more some pure mathematics. There is a proof for that, but we'll just suffice to say there's a proof for that, but we'll just use this demonstration as our proof. So continuing a continuous function, so it has to be continuous, is differentiable on an interval if the derivative exists at every point on the interval. All right, so in order for a function to be differentiable on an interval, maybe it's the entire domain or maybe it's just between a and b, it has to have the derivative at each point. And we remember a function is not differentiable at c if the function comes to a sharp point. So at these different values, there's no derivative there. So it's not differentiable at those spots. And if it has a vertical tangent line. So these x values, here, 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 and here, would be called singular numbers because the values of x for which the derivative does not exist are called singular numbers. And if the left-hand derivative and right-hand derivative of a function are equal when x equals c for a continuous function, so we're still talking about a continuous function, then the function is differentiable at x equals c. So if the left-hand derivative and the right-hand derivative are equal for a continuous function at x equals c, then it's differentiable at x equals c. So notice here really quickly, as we look at the derivative of this line, it's a positive tangent line all the way up until this point. Over here, this is a negative tangent line to the right of this point. So it's not differentiable at x equals c. So we're going to use this idea quite a bit here, or a few times in these next few examples. It says that use the left-hand and right-hand derivatives to determine if f of x equals the absolute value of x minus 2 is differentiable at x equals 2. Well, we're familiar with the graph of absolute value function. This is an absolute value function moved to the left, moved to the right 2. So we have a v here at 2. The left-hand derivative, so the derivative to the left of this point, is negative 1. So the slope over here is negative 1, or the derivative of that part is negative 1. The derivative of this part, or the slope of this part, is m equals 1. So are they the same? No, the left-hand derivative and the right-hand derivatives are not the same, so therefore it is not differentiable at x equals 2. All right, jumping to the next example. For what values of x is the piecewise function shown below differentiable? So for what values of x is this differentiable? Well, let's just think about these individual functions at first. X squared, it's a parabola, that's always differentiable. It's a polynomial, it's always differentiable. 2x minus 1, that's a line, that's always differentiable. The slope, in fact, is always 2. So the only part in question here is when we switch from one function to the other, which is at 1. So what we have to do is we have to see, does the derivative just to the right of our point equal the derivative just to the left? So it is continuous, as we see here in the graph, but we need to see if it's differentiable. So when we check something like this, what we want to do is we want to check both parts. So we'll take the derivative is going to be equal to 2x when x is greater than or equal to 1. So the derivative of this was 2x. The derivative of this is 2 when x is less than 1. So let's look at what happens at 1. So when you plug in 1 here, you get 2. When you plug in 1 here, you get 2. So in both cases, right where they meet at 1, they're the same derivative, so they are differentiable. So for what values of x is the piecewise function shown below differentiable? Well, for all values of x. And again, the reason for that is, say, of x. We know that the entire squared function is differentiable. We know that the entire line is differentiable, so the only point, so that gives us most of the points, all but one, so we have to try out one, and it did work because the derivative was the same when we plugged in that point in question. All right, our last example here. This is going to look similar to some stuff that we did before. So let f be defined as follows. So f of x is a piece function. It equals the absolute value of x plus 3 when x is less than 1, and it equals ax squared plus bx when x is greater than or equal to 1. Find the values of a and b such that f is continuous and differentiable at x equals 1. Well, we've already done things like this where we found that they're continuous. So we're going to still do that same thing, but then we also want it to be differentiable. So here, this graph, this part of the function is set. There's not an a and b in this top part. So we know what this looks like. So that's what we have graphed right here. Absolute value of x plus 3, the absolute value function moved up 3. And we want that when x is less than 1. So we look at 1, we only want it to the left of 1, and we have an open circle here. What we want now is for this function to be continuous. So we need this parabola. Now this isn't any general form because there's not a plus c out there. We want this parabola to hit here. So there's many parabolas that go through this point. It could look like this, or it could be more spread out like this, or it could look like this, or maybe it's just part of the parabola that keeps going up like that. So we have a lot of different options for the parabola to be continuous. But we also need it to be differentiable and fit this equation. So what we're going to do, we want it to be continuous. So in order for it to be continuous, that just the functions have to be equal to each other at our point in question at 1, which is right here. So what we want to do is we just want to plug 1 into both parts. So part 1, or the top part, we're going to put the absolute value of 1 plus 3. That is equal to 4. So we're putting it in here. And put 1 in here. We're going to put a times 1 squared, which is 1, plus b times 1, which is 1. So it has to be equal to a plus b. Now, in order for it to be continuous, these things have to be the same. So this and this have to be equal. So a plus b must equal 4. And so we have all kinds of options. A could be 0 and b could be 4. A could be 1 and b could be 3. A could be -2 and b could be 6. So we have all kinds of options for that, for continuous. But we also need it to be differentiable. So in order for it to be differentiable, what we need to do is find the derivatives and set them equal to each other of the two different parts of that function. All right, so what we want to do is we want to take the derivative of both of those parts. Now, the derivative of this for our part in question where 1 is just this slope right here. So for part 1, we actually don't have to be concerned about this part of the graph. So we're just looking at this. So the derivative is just 1 because the slope is 1 here. For the second part, so for this part, we have to take the derivative, which is 2ax plus b. So we took the derivative of this. Now we want to plug 1 into here because we want it to be differentiable at 1, so we have to plug in 1 here. So this would be 2a putting 1 in for x, plus b. And we want these to be differentiable, so 2a plus b has to be equal to 1. This one must equal this one, just like this one had to equal here. And now what we have is we have two equations with two variables, and we can solve. So we have a plus b equals 4, 2a plus b equals 1. Let's go ahead and subtract. I'm going to subtract this one, actually the upper from the lower, so I'm going to change the signs here, and then we'll just add actually. So we got 2a plus negative a is a, that's 0, equals negative 3. So a has to be equal to negative 3, and that means we can find b by plugging in here. So we have negative 3 plus b equals 4. Add 3 to both sides. It's a terrible looking 3. Add 3 to both sides, b equals 7. So find the values of a and b so that f is continuous and differentiable. A equals negative 3. B is equal to 7. If we wanted to, we could go ahead and put that in here and see what that function looks like. So it would be negative 3x squared plus 7 times x. And if you did put that in there, it would look like this. So here's the absolute value function, but then right here at 1, it has to have the exact same slope at 1. So it's continuous, but it has to have the same slope. So it comes up, continues at 1, and then it actually comes down and changes direction. But it is continuous and differentiable at x equals 1.